solution over some maximal time interval 0 t star. And you can prove that, okay, t star, that's the maximal time of existence of the smooth solution. That's the maximal smooth solution, in the sense that I gave in the theorem. This maximal time it's finite or infinite, right? If it's infinite, you have global in time solutions. If it's finite, you have just local. And it's easy to see that if this maximum time of existence is finite, then you should have a blow-up of the HS norm of u of t. Okay, as you go closer and closer from the maximum time of existence, if it's finite, then this HS norm should explode. Okay, so that's classical. Like for these. But actually, you can do much better. Sorry, there's something missing. This link sub should be infinite. Okay. So, actually, you can do much better than this blow-up criterion. Okay, so this criterion can be much improved. And this is a celebrated result of Bill Kato Maeda. This is a theorem that tells you that if the maximum time of existence of the smooth solution is finite, then this implies that the integral from 0 to t star of the L infinity normist in space so the L1 norm in time of the L infinity norm in space of omega, where omega is the vorticity, should blow up. I remind you that omega is the curl of the velocity field, the so-called vorticity that we had seen yesterday. Okay? So it's a much better criterion because you see this criterion involved the HS norm, so a lot of derivatives. Okay? Whereas here you only have to check something on one derivative, and more precisely on a special combination, which is the vorticity. Actually, it's not hard to replace omega by the gradient of u. It's easy to see that if the gradient of u in an infinity blows up, then you, it's a criterion for local existence. But the strong point here is that not only you have something with first order derivatives, but it's the vorticity. Okay? And as we have seen, vorticity in 2D behaves very well. Okay? So consequence of this theorem, okay, so for a proof again you can see the book by Maeda and Bertolzi.
is for
Oh, that's for Euler. Thank you. Or at least it was stated for Euler, but okay. Works as well for many others. So, what is the consequence of this result? In 2 dimensions, you have the transport equation for vorticity, right? We had seen that the vorticity obeys a simple transport equation in 2D, which means that omega at time t in L infinity is the same as omega at time 0. Right? The L infinity norm is preserved by transport. For all t less than the maximal time of existence. But then, there is no way that for a finite t star, this quantity can explode. Right? Because it's just t star times the L infinity norm of the vorticity, of the initial vorticity. So it gives you by the BKM, the B cat omega criterion, it gives global existence of a smooth solution in 2D. Okay? Global existence of a smooth solution in 2D. This is for Euler. And it can be adapted, as I said, to Navier-Stokes. Okay. So in 2D, smooth solutions are global in time. So that's the main thing about 2D flows. And the key point is that the dynamics for the vorticity is much simpler. So what about 3D? So for 3D flows, nobody knows. Okay? So for Euler, there is no result. Nobody knows about global solutions for 3D Euler. For Navier-Stokes, there is no result, and if you find one, you win, and million. There is no result for large data. Okay, so my conclusion is that for Navier-Stokes you can do a little better than for Euler. You can prove that for small data, small smooth data, you have no body time solutions. It's not hard. To prove a theorem of this kind. I mean, of course, you can prove much more, but I will give you an example of such a global theorem for small data. So, I won't have time to prove it, but it wouldn't be so hard. The theorem tells you if you let mu strictly positive, you are in the Navier-Stokes case, right? You take, as before, some initial data in HS sigma, with sigma strictly, with S, sorry, strictly greater than d over 2, that's 3/2 plus 1. So, as I showed, there is a local in time solution, there is a maximum solution, and if the initial data is small enough, solution will be global. That means there exists some epsilon depending on mu, the viscosity coefficient, such that if the HS norm of u naught is less than epsilon, then the maximum time of existence of the solution is infinite. So that's a picture for this smooth solution.